So let's talk about transformer circuits. So how we do the math on a transformer circuit, and I'm going to look at current, and I'm going to look at voltage, I'm going to look at turns ratio, and we're going to look at symbology as well, which is important, and I'm going to talk about reflected resistance. So this circuit shows us the symbols that we're going to see in transformer circuits. What's going on here is I've got my power supply. Obviously it's an AC power supply because we know these do not work on DC, so we need an AC power supply here. You know, I'm going to label it 60 Hertz, and just the reason I'm doing that is just to indicate that's why I'm using an iron core transformer. Yeah, and we know the iron core transformers are those solid lines. If I were to do this and make a dotted line on both sides, then I know that is a ferrite core, and we use ferrite cores for much higher frequencies. But anyway, so I'm going to continue with this because this is a power transformer, and we're looking at really essentially a 60 Hertz signal, something that we would see from the power system. Now, I've got this at a low voltage. It's a good number I can work with, and if I wanted to, I could make that 120, and then I can work from here. We do have a turns ratio of 10, so I'd actually have 1200 volts over here. But I want to work with more tangible values, something that we're used to working with. So I'm just leaving this with 10, and we're going to look at how to figure out what the voltages are. So first, let's continue with voltages, but first let's kind of unpack the symbology of the actual symbols for the voltage. So on this side, this is the that value there is the voltage primary, and this value over here is the voltage secondary. So the voltage secondary is seen across here, and the voltage primary comes out of here. So this side of the transformer sees the voltage primary, and this side is producing the voltage secondary. Cool. So we have that. Now, as far as the current goes, it's the same thing. So I'm going to draw the current like this because we know it's AC. It goes both ways. This is going to be the I primary, and this is going to be the I secondary. Now, those currents are going to be different. These voltages are going to be different. Again, it only works with AC. These do not work on DC. Okay, so we have our load over here, which is 100 watts. What I want to do is, I want to do some calculation. I want to find out actually what the voltage is over here. I want to know what the currents are as well, and we're going to look at the reflected resistance. We haven't even calculated the resistance yet, but that's kind of a step we'll get to in a minute. So let's just jump into finding out what the turns ratio is. Now, we've got this guy here. This is a symbol, or this particular nomenclature is not, it's not really a ratio. I mean, I don't like to say it as a ratio because watch this. If we go back to like grade 7 math, we know that if we write that ratio 1.6, we know that equals 1 over 6. Well, just forget about that. Just don't even consider that as a ratio anymore. The thing is, that is just a nomenclature to indicate the number of turns on this side, and there happens to be a semicolon in the middle. Just look at it that way. Is that a semicolon or a colon? Anyway, let's continue. So, what's going on is that's a semicolon. And then let's continue here, and we'll say, I'm going to forget about this, forget about what I learned in grade whatever math, and I'm just going to understand that this is telling me what the turns ratio is. Now, how do I figure out what that n is? Essentially, that n is a fraction, just like I drew that 1 over 6. The n can be 1 over 6, actually, but we do it a little bit differently. Get this. We know that the n, in this case, the n is going to actually be equal to 10 over 1. Yeah, so when we want to find the n, which is the turns ratio, I'm going to have this number on top of this number. And the reason we do that is because the nature that we look at these things is through the viewpoint of the voltage. Because ultimately, their big thing is that they step up voltage and down voltage. More specifically, they transfer power, AC power, from one form to another. Really, the power on this side is the same as that. So let's actually do this over here. So we're going to say the power primary, and this over here is the power secondary, and we know that's 100 watts. So actually, really, this is going to be 100 watts as well. So that we can actually use that to help us calculate a lot of stuff. But what I'm saying here is that the power here is voltage times current, and the power here equals voltage times current. And we know that these two equal each other because the power on this side equals the power on that side. So if I'm going to say that the voltage goes up, now if this voltage, the primary and then the primary, and that's the secondary and that's the secondary, if I'm going to say that this voltage went higher, for the power to stay the same, the current has to go lower. Yeah, so what's happening here is that if I look at this, and again I'm talking about why this number's like this, and why this N is like that. If I'm looking at this from the perspective of voltage, I know that the voltage is either going to go up or going to go down. The current's going to do the opposite. Actually, if I were to say maybe this turns ratio was all about the current, I actually would do it like this. So if this turns ratio was all about the current, I would do that because I can see that the current, in this case, if this is 1 to 10, that's talking about the voltage. So the voltage is going to go up by 10 times. Well, guess what? The current's going to go down by 10 times. So that would make sense if we viewed these from the perspective of the current. But we don't. We view these from the perspective of the voltage. So it's actually a step up. In this case, it's a step up because it's 10 over 1. So if I were to actually have this differently, if this was a 10 to 1, this ratio would be like this. It would be 1 over 10. And that makes sense because in this case, it's a step down transformer. I have more coils over here, more turns over here than I do over here. So whatever the voltage is here, it's going to go down by 10. Again, it's the perspective of the voltage. Okay, cool. So that's where that turns ratio comes from. So don't confuse this with some mathematical symbol for a ratio that you learned in grade 7. Okay, good. It's just the nomenclature itself indicates the turns, the number of turns here, the number of turns here, and there just happens to be a semicolon in the middle. Okay, so I'm going to put this here and 1 there, and we know that N equals 10 over 1. So when I go ahead and use that in my formulations, I'll just use N. Hey, what's the unit? No, there's no unit. Okay, it's just a ratio. There is no unit. Okay, so let's move forward and unpack what the voltage looks like. Okay, I know the voltage over here is going to be 100 because I'm starting with 10. And by the way, if that was written down as 10 volts peak, then I can calculate the voltage over here with the turns ratio as, in this case, 100 volts peak. And if this was peak to peak or RMS or whatever it is, but if it's not labeled, if it doesn't say volts peak to peak or volts peak, then we assume it's RMS. Generally, we do all of the math with AC circuits in RMS when we're talking about power. It's actually really important when we're talking about power because the whole nature of RMS is kind of all about power. Okay, so let's continue. As far as calculating the voltage over here, I know it's 100, so how am I going to do it? Well, I'm going to do this. There's a formula here that's got an N in it. So N equals the voltage secondary over the voltage primary. That's the formula to count. So it's the formula that establishes the relationship between the voltages and the turns ratio. So in this case, I want to find out what the voltage secondary is, so I'm going to solve for that. So I'm going to say voltage secondary is going to equal N times voltage primary, and in that case I'm going to say 10 times, now the voltage primary is 10 volts. I don't have to write 10 volts AC, I don't have to write 10 volts RMS or anything, it's just understood it's RMS. So in this case, I'm going to write 100 volts. So my secondary voltage is 100 volts. Okay, so there you go. So now we know what the voltage is over here. I'm going to label it. So I'm going to label over here 100 volts. Okay, so we know our voltage here and our voltage there. Now let's take a look at the current. So the current formula is actually just the opposite of this. It's this. So let me write it over here, and you'll see a problem very quickly. So I'm going to say N equals current primary over current secondary. So the reason for that is because, again, we're looking at this from the perspective of how a transformer does the voltage. So in this case, it's either a step up or a step down. In this case, it's a step up. So, but our turns ratio is larger. This N will be greater if it's a step up voltage. So that means that essentially the current is going to go down. So what we're looking at is, or the current's going to do the opposite thing. That's a better way of looking at it. The current's going to do the opposite thing to what the voltage does. So what we're doing here is we're taking the exact same formula. Whoa, it's over here. It's the exact same formula, and we just flip it upside down. So let's solve for the current. Yeah, well, there's a problem. Take a look at it. We don't know what the current is. I don't know the current on this side. I don't know the current on this side. Ohm's law works in all circuits. Yeah, Kirchhoff's law works in all circuits too. In this case, we don't need to use Kirchhoff's law because, Kirchhoff was all about, hey, let's put a couple components or elements into a circuit and see what happens. We've only got one here. But Ohm's law works. So I can calculate the current through here. I can calculate this current, but I don't know it, but let's calculate it using Ohm's law. Well, in this case, how I'm using Ohm's law is I'm using the power formula. And we unpacked the power formula and really ultimately said, oh, it actually comes from Ohm's law. Yeah, so I'm still using Ohm's law, but what's going to happen here is I'm going to find the current through here by doing this. I know that power equals current times voltage. So if I get specific about the power in this side, I have to use proper subscripts. So I'm going to say the power, the secondary power, is the secondary current times the secondary voltage. So in this case, I'm going to rearrange that. I secondary equals, in this case, voltage secondary over power secondary. And in that case, so this is pretty easy here. I've got 100 and I've got 100, so it looks like it's 1 amp. Okay, so I'm going to write 1 amp. So I'm going to write over here 1 amp. Okay, good. So now I'm going to get rid of that so we can move forward. But that was a nice, easy kind of, quick fix. So in this case, I'm going to use my turns ratio to find my current over here. Okay, so I need to calculate the primary. So my I primary is going to equal N times I secondary. In that case, it's 10. And the I secondary is 1 amp. And that equals 10 amps. Okay, let's talk about this. Does it feel right? I mean, the voltage seemed to feel right. We know it's a step up, and it's, it's times 10, so yeah, we're fine with that. The current, what should it do? Well, the current should be actually stepping down. So when we talk about stepping up or stepping down, we look at it from the perspective of the source and what's happening through the transformer. Is it going up or is it going down when it comes to the other end of the transformer? And we can do that with voltage or current. So in this case, we want to just kind of make sure. In this case, we know the current was going to go down, and the current in this case is 1 amp. So it should have been higher. So actually, yeah, that does make sense. So always go through that process when you calculate anything. Always kind of say, does that make sense? Does it feel right? In this case, yeah, it feels right. It's actually good. I mean, yes, I did choose numbers that were really easy and we could work with, but essentially you can kind of ballpark it and you can kind of say, well, it's got to be around, it's got to be bigger or smaller, and kind of get a feel for that. Okay, so let's continue. What I've got here is we have solved for the voltage on either side. With the voltage over here using the power formula, we solved the current on this side. So we solved the secondary current. And then from there, I was able to take the turns ratio formula and find the primary current over on this side. Okay, that's good. So now, what do we do next? Well, what I want to do is actually calculate the power on this side, just to show it's the same. Kind of actually, it's another step that helps us kind of go like, okay, did I do this right? Because again, sometimes these are complicated. So the power primary is going to equal the current primary times the voltage primary. In that case, we're looking at 10 times 10, which is 100. Yeah, we got 100 over here, so that's good. I'm not even going to complete that. But it was just more of an intellectual kind of walk through, okay, just to check my work. Okay, good. So it looks like I've got the right current, I've got the right voltage and stuff like that. So let's unpack the resistance. Now, so I want to talk about reflected resistance. Now, in this case, I've got a couple different ways that I can solve the resistance on this side, or I could solve it on this side. When we talk about reflected resistance, it's really about what resistance this guy sees over here. Really, like what, as far as it's concerned, how much work or how much resistance is it kind of feeling when it has to run this system, what does it think this is? Remember, it doesn't see this. It's not actually coupled in any way. Well, it's magnetically coupled. Does that make sense? There's no electron connection. The electrons on this side don't go into this side. So what's going on is that the magnetic field couples these together, these two things together, but this doesn't actually know what the step up or step down is. It doesn't know. But it can feel a certain resistance on its side. What is that resistance? Well, in this case, it's not whatever the resistance of that light is. Let's calculate that resistance of that light. So we have a couple different ways to do it, right? So we could do this. We know that power equals V squared over R, and that could be my secondary and secondary and secondary, and then I could solve for that, or I could actually use Ohm's law here. Let's actually use this one because I've already used Ohm's law in an example. So I'm going to do this. I'm going to rearrange this, and I'm going to say the resistance. Now in this case, I'm not going to call it secondary of the load. The resistance of the load in this case is going to be the voltage secondary squared divided by the power of the secondary. In that case, that's 100 squared divided by the power, which is 100. Sorry, 100 squared divided by the power, which is 100. So 100 squared over 100 equals 100. Isn't it? Let me do the math. 100 squared divided by 100 equals 100. Yeah, it's always good to double check, even if your brain says, "Yeah, I know that." I mean, if it's really simple, that's actually really simple. But I thought I'd go through that process anyway. So in this case, this is 100 ohms. So the resistance of this is 100 ohms. Okay, that's fine. You know what? I'm going to double check that with Ohm's law. I know that I equals V over R, so therefore R of the load is going to equal the voltage secondary over the current secondary. In this case, that's 100 divided by, in this case, 1. So yeah, that is 100. So I got to 100 ohms again. It's always good to double check. Okay, so moving forward, we know the resistance of this bulb. How does this see that resistance? Does it see it as a higher resistance or a lower resistance? Then we have to kind of think about that. And then I will show you the formula to calculate that, because there's just a formula to do that. It's pretty simple. But again, get a feel for it. Okay, in this case, I know that this is a step up. Okay, so that means the current's a lot higher on this side and the voltage is really low. Okay, so in this case, the voltage is higher and the current is really low. So let me just think about that. If the power is the same, then essentially the current being higher over here with lower voltage. Okay, so if I needed to have a certain amount of current going through a load, and it's actually pretty high, it's 10 times higher, okay, and with a lot less voltage, it's only 10 volts. My resistance has to be a lot smaller. Think about it. We know that the current goes up and the resistance goes down, and in this case the current is a lot higher, and the push, that energy, that pressure, or what we call the voltage, that's actually making those electrons go, making that current go, it's just like a wimp now. It's like 10 volts. So it has to be extraordinarily low resistance to allow that amount of current to go through. Remember, the current is the resistor, or the load is the boss of the current. So if that load is drawing 10 amps, it must be ridiculously low. So that's what we're going to find in our math. So let's actually do that formulation. What I'm going to do is just clean this up a little bit. Okay, looking at the reflective, this is how we calculate the reflected resistance. So essentially, it's kind of the same thing. It's N, just bear with me, I haven't finished this yet. N equals the resistance over the resistance. So which resistance do we put here and which resistance do we put there? Well, it's along the same lines as the voltage. So we're studying what's happening with the voltage and the perspective again. Why did we make the voltage secondary on top and the primary on the bottom? That's because we're doing the perspective of the voltage. So in this case, we're keeping that perspective and we're looking at the perspective of the resistances. So in this case, this is the resistance of the load, which is the secondary side, and this is the resistance reflected. Now, not finished. Ready? Watch this, is pretty cool. Squared. So, I did do a video on reflected resistance. More specifically, it was the physics of the reflected resistance. And I walk through the formulation of why this actually exists. So if you want to watch that video, it's a great video. It really is, it's a tangible video about why this happens and why this reflected load is squared. It's weird. Yeah, but I went through the kind of almost the physics of it. So you can watch that video. But what I'm going to do is continue here, and I'm going to say, okay, so if I want to know what resistance this thinks that is, how it sees it, then I'm going to rearrange my formula over here. I'm just going to do it over here. So I'm going to say R resistance load is going to equal R of the load itself divided by N squared. So in this case, we know that guy is 100 ohms, and this guy, that N, is 10 squared. Oh, that's a really low value. Yeah, it is actually. Watch this. So that's actually 0.1 ohms, or remember, we do not write numbers in engineering that start with a 0 because we have these things called metric prefixes. So that your calculator shouldn't even tell you that. Yeah. So I'm just going to actually erase that. But if you're not using your calculator, which you don't actually need to use here, then you should actually know that this is 100 milliohms. Again, never ever write a value down that starts with a 0 or a decimal because we have these things called metric prefixes. And the reason they exist is so that we don't have to write values that start with 0. Yeah, they also exist so we don't have to write values with lots of zeros. Okay, I'm not going to go on about that anymore. So we've talked about reflected resistance. We know how to calculate that. You know how to draw the circuit. You know the symbology. We know the different types of symbols. If you don't know, we talked about the ferrite core for higher frequencies, and we get into frequencies like 10,000 or 100,000 hertz or even higher. Then we're going to get to an air core where there are no lines. Okay, cool. Well, I'll put these back. Okay, good. So we know what's going on. We've covered everything. I don't think there's anything else I need to cover. You understand the math, how to calculate this stuff. It doesn't actually get more complicated than this. And if you just want to remember what I just did, it's a matter of making some circuits up and just practicing. Okay, bye.